This is averaging theory for weakly nonlinear oscillators in section 7.6 of Strogatz. So we're going to consider systems of the form that look like a harmonic oscillator plus some small perturbation. So x double dot plus x. If I set that equal to 0, we have the harmonic oscillator, but we won't do that. We'll say there's some small parameter, epsilon, times some function of x and x dot equal to 0. Epsilon is much, much less than 1. So this is a perturbation of the harmonic oscillator. And we like to do that because we know everything about the harmonic oscillator. So we just want to know, how do things change a little bit? So we will start by writing this in the usual phase space coordinates of x and y. So we would say x dot equals y, y dot equals minus x minus epsilon hx. X dot. Note, what is h of x? X dot. For the van der Pol oscillator, it's x dot x squared minus 1. In general, this is going to be nonlinear. We could look at other things too, but just note that. Now, when epsilon equals 0, we know the solutions. Again, it's the harmonic oscillator. I'll write it differently than before. The solutions are x equals a constant r times cosine t plus v. So now we're including the possibility of a phase, and we're calling the amplitude r. So if that's what we had for x, then what we have for y is negative r sine t plus v, where r and v are constants along trajectories. Now, when epsilon is not equal to 0, just like we saw in the simulation for the van der Pol oscillator, we expect a slow drift of r and phi. But trajectories will be nearly circular. At each moment in time, they'll be almost circular with a period, almost coming back, of nearly 2 pi. So now we're going to allow, for the case of epsilon not equal to 0, we allow the possibility that r and phi are functions of time. We now are going to define r as a function of time and phi as a function of time, such that x as a function of time is r as a function of time times cosine t plus phi as a function of time, and y is negative r sine t plus phi as a function of time. You might be worried that, well, hold on, y doesn't look like x dot, but this is more of a definition of r and phi than it is saying anything about time derivatives. So we're basically saying r is square root of x squared plus y squared, and that tangent t plus phi t is a way to define that angle. And there's a negative sign because of the negative sign there. So this is y over t for x over t. We'll find equations for r dot and phi dot. So how r and phi change in time. Find equations for r dot and phi dot. So how do we do that? We could start with this definition. It's easier to write in terms of r squared equals x squared plus y squared, and then take a time derivative of that. So r dot equals x dot plus y dot, and then use what we have up above for x dot and y dot. Okay. What is this? This is x times y plus, this is negative x times y, negative epsilon y times h. And so these two terms cancel out, and we're left with negative epsilon y h. But we'll write that in terms of our assumption of what y looks like. So this looks like negative epsilon, negative r sine t plus phi times h. These two minus signs cancel out. We get epsilon r h sine t plus phi. Okay, and this was r times r dot. Cancel out the r's. So this leads to r dot equals epsilon h sine t plus phi. It's an ODE for how R evolves. We could similarly get the ODE for phi dot. We take this expression over here, rewrite it a little bit, take the inverse tangent. We take d by dt of, I guess you could say, a tan 2. We want the 4-quadrant version, and we'd have that equal to d by dt of t plus phi of t. So, on this right-hand side, we'll get a 1 plus phi dot. And then if you work out what this left-hand side gives you, you'll eventually have to plug in x dot and y dot. You'll get a 1 plus epsilon h over r cosine t plus phi. The ones cancel. So we get phi dot is epsilon times h over r cosine t plus phi. Good. We've got what we expected. We would get differential equations for a slowly varying amplitude and phase. We've got r dot and phi dot are both of order epsilon, which doesn't mean we'll set them equal to 0, but that's what we've got. And so that's good. We're on our way. Now, what about h? H shows up in both. So h, which is a function of x and y, since y is equal to x dot, we can now plug in our assumption for what these look like. And I'm dropping the dependence on time. So this is h of r, which is time varying, cosine t plus phi, and then negative r sine t plus phi. And we could turn our system for r dot and phi dot into something that we can solve, maybe even use the methods from before, like either 1D ODEs or maybe phase playing for these slowly varying things. So now we're going to use the idea that we have a separation of time scales. We've got fast oscillation. So in the phase plane, things are going around quickly, right? They go around approximately coming back every 2 pi. And so the two time scales are, we have fast oscillation. So it's, time of about 2 pi, which is actually of order 1. And then a slow drift of this amplitude and phase, which is going to be of order epsilon. It moves slowly compared to the oscillations. So what we'll do is average out over the fast oscillations. For these ODEs, we'll average over one cycle, approximate cycle of 2 pi, one oscillation. And by oscillation, I don't mean that it's coming exactly back to itself. It's just sort of going around. Think of the polar coordinates. It's just sort of going around roughly once. So average over 2 pi. And the notation, just to be clear, it's sometimes written as G bar or these triangular brackets. Given G as a function of time, we could do this average. So we first divide by the period, and then we could do t minus pi and t plus pi and take the integral. Effectively, what we're going to get left with is sines and cosine averages over a cycle. And then we could just either look up things that we've already calculated about sines and cosines. But that's sort of where things are heading. We'll derive equations for average of r dot. There's another thing that we need to note. If you take the derivative and then the average, it doesn't matter what the order operations are. D by dt of the average of something is equal to the average. And you could show that. It's by the fundamental theorem of calculus. So order of averaging or time derivating doesn't matter. So here's our plan, is we will derive equations for r bar, not r vector, time average of r dot. So how is the cycled average amplitude changing? And also how is the cycled average phase changing? So what we get is r bar dot equals, we'll take the time average of the right-hand side of the ODEs. So that was epsilon h sine t plus phi. And phi bar dot is time average epsilon h over r cosine t plus phi. And we're going to make an assumption here. So the right-hand side depends on r and phi, not r bar and phi bar. We're going to assume that over one cycle, r equals r bar plus something of order epsilon, and phi equals phi bar plus something of order epsilon, some change of order epsilon. So everywhere in these, the averaged right-hand sides, we'll replace r and phi by r bar and phi bar. So this will cause an order epsilon squared error in the ODEs, but that's all right. Order epsilon squared is small. We're trying to get the order epsilon. So we will replace r and phi with r bar and phi bar in these right-hand sides. The beauty of this is that we will get autonomous equations that we can then analyze with phase plane methods. So that's good. That's what we want. Let's do this. We'll do this for particular problems. We got the van der Pol system. Let's do that. I guess there's something else that should be said. Our approximation, we treat r bar and phi bar as constants when performing the averages over one cycle. So let's try on the van der Pol oscillator. Van der Pol, well, I should say van der Pol equation. We don't know if it oscillates. Well, we do. We know. So for the van der Pol equation, we've got h of x and y is y x squared minus 1. So h y x squared minus 1. And then we substitute in what we have for y and x. We've got negative r bar sine t plus phi bar times r bar squared cosine squared t plus phi bar minus 1. And maybe there's some order epsilon correction to that. We'll write the ODE for r bar dot. So this gives us r bar dot equals, and let's just write time average, epsilon h sine t plus phi bar. And doing our bookkeeping, will be an order epsilon squared error. Let's just work this out. We've already written h, so now we've got negative epsilon r bar. There'll be a sine squared t plus phi bar times r bar squared cosine squared t plus phi bar minus 1. Time average of all that. Let's pull out things that are constant, right? For purposes of taking the average, r bar is constant. So we can pull out these r bar things and epsilon. So we got negative epsilon r bar squared times, I'll just write it this way. Phi bar, since it's a constant phase, it's a constant number, so it's like a constant phase. It won't change the average. It does a time shift of taking the average. I'll use this notation of just sine squared cosine squared. We're just doing an average of that over 2 pi minus sine squared. Doing our bookkeeping, forgot some bookkeeping, right? Order epsilon squared be the next term if we were to continue this expansion. So we've already figured out, hopefully by a technique that you don't think is too dumb, what this is. The average of sine squared is 1/2. We already did this too. Turns out to be 1/8. And now we can just substitute back in. And what do we get? So we've got r bar dot equals negative epsilon r bar squared times 1/8 minus 1/2 plus things of order epsilon squared. Let's collect some terms to make this look a little bit prettier. R bar dot equals epsilon r bar over 8 times 4 minus r bar squared plus order epsilon squared. For purposes of analyzing this, we're just going to neglect this part. And notice this is an ODE for how r bar changes in time. So how the slowly varying amplitude changes in time. It changes very slowly because there's an epsilon in front. And we can use the 1D graphical method. So that's really cool. We'll plot the vector field, r bar dot versus r. This looks like things that we've seen. There's going to be a curve, it reaches a maximum, and then it crosses 0 at 2, it's looking like arrows are moving away from the origin and then to the value of 2. This is 2. So now we not only know that the amplitude of the van der Pol oscillator goes to 2 in the limit of small epsilon, we have some idea of quantitatively how it does that in terms of this average amplitude. We've got that R bar goes to 2, stable point, as t goes to infinity. It's asymptotically approaching that. So amplitude of the van der Pol oscillator goes to 2 for, remember, we're in this limit of epsilon is small. We can even analytically solve this ODE. It's useful to have some initial conditions. If x at time 0 is equal to 1 and x dot is equal to 0, so if we're thinking of where are we in this phase plane, starting here at that point of the original coordinates, then we get that R bar 0 is equal to 1 for this 1D ODE, and we can solve the R bar dot ODE. Right, we could do separation of variables. We get t on one side and everything depending on R on the other side. If we solve this, what do we get? R bar as a function of time is equal to 2. It's for these specific initial conditions over square root 1 plus 3 e to the negative epsilon t. So that negative epsilon t shows how slowly things happen. And for different initial conditions, you'll get something different. I mean, this shows as time goes to infinity, this becomes 0. And so we're just left with R goes to 2. We've only done the amplitude. What about the phase? Phi bar dot equals epsilon h over R bar cosine t plus phi bar. And if you want to, you could drop the bars. We'll pull out constant things, epsilon over R bar, and then plugging in what h was, have negative R bar sine t plus phi bar times R bar squared cosine squared t plus phi bar minus 1. All of that times cosine t plus phi bar. And then thered be a plus order epsilon squared. That's for proper bookkeeping. All right, so what do we get? Negative epsilon R bar squared cosine to the third sine. The time average of that minus the time average of sine and cosine. It turns out if you have an odd power of cosine or sine times an odd power of cosine or sine, other than sine squared, cosine squared, but both of these equal 0, the time average. So it means it's above the 0 as much as it's below the 0 over the 2 pi. So those are both 0. So we get, I guess if we were to keep doing bookkeeping, at least to order epsilon, this is 0. So if we want, phi bar dot is something of order, if it does change at all, it'll be in order epsilon squared. What does that mean? That means phi bar changes on a super slow time scale of order 1 over epsilon squared. Right, 1 over epsilon squared, we say super slow, that means a super long. So if it changes order 1 on a time scale, that's 1 over epsilon squared. So if epsilon is very small, 1 over epsilon squared is very, very big. If we were to return to, what does x do? We could look at what x does. So go back to x. X as a function of time equals, and I'm just going to drop the R bar, drop the bars. This is R as a function of time, cosine t plus phi as a function of time, but that's 0. So we're left with, at least for the initial condition, same initial condition as before. We've got 2 square root 1 plus 3 e to the negative epsilon t times cosine t, plus things that could be of order epsilon. But what does this give us in terms of a plot? If we were to plot as a function of time, this part gives us the sort of envelope, and this part gives us the oscillating. I'm going to plot plus or minus 2. We're starting at 1, and here's minus 1. That envelope increases and then just sort of asymptotes to 2 in both directions. And the fast oscillations will be something. So this is qualitatively in blue what the trajectory looks like. The oscillation should all be looking the same. This magenta curve, this is the envelope. So it gives the amplitude. So that's what we would get. So averaging is this powerful tool. The book talks about other procedures as well. It talks about using two timing. If you assume from the beginning that there's two time scales in an ODE, then you could take derivatives with respect to the different time scales. I'm not going to talk about that. You could read about it. He calls it two timing. It's also called the method of multiple scales. But I find it spooky and am not terribly excited about it. At some point there's leaps of logic. I think doing it this way in terms of averaging makes more sense. Another common example is something called the Duffing equation. And I forget what Duffing was working on, but it looks like x double dot plus x. So, what do you know? Looks like harmonic oscillator plus something small, x cubed equals 0. So in some sense, this looks like, if you think of the usual Hooke's law, this looks like Hooke's law would be if there's a displacement x, then the restoring force is linear. So you would have something like that, Hooke's law for spring. And this shows deviations from Hooke's law. So if you have epsilon less than 0, you get this sort of curving downward. And if you have epsilon greater than 0, you have curving upward. That means curving upward would mean a stiffening spring. So as you pull the spring harder, it's not just a linear, the restoring force isn't linear in that displacement. It actually gets stronger and stronger. Epsilon less than 0 means a softening spring. So we've got that. Just looking at this, putting it in the form that we've been considering, x dot is just equal to x cubed. And so using what we've assumed, we assume the same thing for all of them. So x is going to be r cosine t plus phi. So we could do that again. So this will be r cubed cosine cubed t plus phi. And then you get, again, I've dropped the bars. So it's understood when I write r dot, this is the time rate of change of the fast oscillation averaged amplitude. Epsilon h sine t plus phi, which equals, pull out epsilon and r to the cubed. What do we have? Cosine cubed sine. We've seen that already. And that averages to 0. So what do you know? If we do our bookkeeping correctly, that was just the order epsilon. So this thing changes, if it changes at all, it changes on a very, very slow time scale. So R is constant, roughly constant. If we do the same thing for the phase of the Duffing equation, that's epsilon h over R times cosine t plus phi. This becomes epsilon r squared cosine to the 4th plus terms of order epsilon squared. Cosine to the 4th, so that would be like a whole bunch of oscillations. And it averages to something slightly less than a half, turns out. Right? You could do this integral if you want. It's 3/8. So it goes up to 1, but it averages to 3/8. So we've got phi dot equals 3/8 epsilon r squared. So here we do get that the phase changes, and interestingly, the amplitude does not. So if you think of starting with some amplitude, we'll call it A, capital A, instead of R. So if initial amplitude is A, phase changes like phi dot equals 3/8 epsilon a squared. And what's the frequency? The frequency is the time derivative of the thing inside t plus phi. the frequency of oscillations, omega, is d by dt of t plus phi. That's 1 plus phi dot, which in this case is 1 plus 3/8 epsilon a squared. It's sometimes easier to think of that in terms of the period of oscillations. Capital T, it's 2 pi over omega. And using a hopefully well-known Taylor series expansion for 1 plus something small raised to the negative 1, you get 1 minus 3/8 epsilon a squared plus maybe some other things of order epsilon squared. But to leading order, you get the period of oscillations depends on the amplitude. Now, interestingly, the pendulum fits the Duffing system. What do I mean by that? For the pendulum, this is the normalized pendulum, so rescaled, right? The pendulum equals negative sine theta, which to leading order, maybe I'll write it this way, write it in the plus equals like that. If we do a Taylor series expansion of sine theta, what do we pick up as terms? We get first theta and then minus 1/6 theta to the third plus things that are of order theta to the fifth. If we're making a kind of small angle approximation, then we could neglect these. And then this looks exactly like the form we care about. So it looks like our perturbed harmonic oscillator with h equal to theta cubed and epsilon equal to a specific number, which I don't know if you want to say that's small. You might even be upset that it's negative. Well, it turns out we didn't have to assume that epsilon was positive. So this works, which means we could look at what the period of oscillations is for the pendulum as we change amplitude. We know as you get to very large amplitude, the pendulum is swinging somewhat wildly. So there's a really large amplitude of the pendulum. And this definitely would have a longer period than small oscillations of the pendulum near the origin. Right? And that goes to infinity when you start at just barely near the top, and then you give it a nudge, and that'd be like the largest possible oscillations. For the pendulum, we've got that the period of pendulum oscillations, t equals 2 pi 1, and now we've got minus 3/8 minus 1/6 a squared 2 pi 1 plus 1 over 16 a squared. So the leading order correction for how the period of a pendulum's motion changes with amplitude is given by that formula. So this is saying if we start out here with an initial amplitude of A, this is going to go around, come back with a period that's 1 plus something that's quadratic in A. So if we were to plot that, this would be the period of oscillations versus A. Here's 2 pi. So we start out, the oscillations for small a are all about the same. And then when this cubic term kicks in, you see that this thing will grow. Eventually, it's going to go to infinity. If you think of a equals pi, right, this thing is going to shoot up to infinity. So that's kind of interesting. Looking at the Duffing system, because it mathematically looks the same as the pendulum, we get some information about the pendulum.